It's a pleasure to introduce our first speaker today, Professor Ariel Pacetti from Universidad Nacional de Córdoba. He will talk about on the number of Galois orbits of new forms. Please, Ariel.
Okay, so thank you, Adrian, and the rest of the organizers for inviting me to give this talk. So this was a joint work with Luis Dulefe and Panos Tsagnias. So most of the talks will be handwritten, and there's a few slides I would like to show. So lucky enough, yesterday when I was, well, I already had my talk ready, but I was a little nervous about all the things I had to introduce, but half of the things were mentioned in yesterday's talks by Jessica and Professor Hida. So lucky enough, you will see a lot of things appearing that were already mentioned yesterday. So let me start with some motivation for what we did. So suppose that k is an integer greater or equal than 12, and you take a new form for SL2 of C, so it's a level 1 a modular form, which is cuspidal, and it's an eigenvalue for all the Hecke operators. Then we know that if we take an element in the Galois group of Q bar over Q, and if we conjugate our form, and this part here means that if f has a Fourier expansion of the form an times q to the n, then sigma of f is just the Fourier expansion sigma of an times q to the n. And this is again a new form. And then there is a natural question to try to study. So question, which is the following: what is the number of Galois orbits of such new forms? Okay, so you know that for each given weight you have finitely many eigenforms. Then you can start with an eigenform and look at its Galois orbit, and then try to understand how many Galois orbits there are over there. And there is a well-known conjecture, which is due to Maeda, and I think it's from 97. It appeared in a joint article with Hida in 97, which states that there is a unique orbit. So in particular, all forms are conjugate of each other. Actually, the conjecture is much stronger. It states that furthermore, if you compute the Galois group of the coefficient field of your forms, then this is isomorphic to the symmetric group, where n is just the dimension of Sk, of SL2 of C. And actually, in the article, they show a lot of applications of this conjecture. But so far, this conjecture is completely open. There are many numerical experiments and some heuristics, but we're still far from having some idea why this is true. And so what is our goal? Is to try to study what happens if we replace SL2 of C by gamma naught of n. And so in particular, I'm not considering forms with Neven-types. Studying form with Neven-types is a little different story. And so the idea is introduce some invariants to get a lower bound on the number of such Galois orbits. Okay, and it's a very interesting phenomenon. So Panos was the one who started studying numerically these sort of forms, and so what happens is that unlikely in the case of modular forms with level 1, the situation is not the same for all weights. So somehow what happens is that for small weights there are some like noise that you have maybe many forms or some forms are missing, but once the weight is large enough, then the number of Galois orbits tend to stabilize, and then you expect this number to be the same. But for the lower bound, it really doesn't matter. So let me state our first result, and then the purpose of the talk will be to try to explain what we're talking about and how to handle this. Okay. So the main result is the following. I'm going to put an assumption, and I will explain why this assumption appears. You will see that it doesn't appear in the computations, but it will appear in the end. And we don't expect this to be, this assumption should be easy to remove, but we still didn't. Well, I explain later why we cannot, we have to put it. So suppose n is a prime power or square free. And then our main result is that if you take the product over all primes dividing n of some invariant that I will define soon, this is a lower bound for NCM of nk. And so let me explain what this NCM means. This was already mentioned by in Hira's talk yesterday. So NCM of nk is the number of Galois orbits of newforms of level gamma naught of n and weight k without complex multiplication. So you have some forms which have somehow some automorphism groups, which in a Galois representation, which is bigger, or a lot of Fourier coefficients are zero. You can check the complex multiplication computation. When you look at your form, you can tell whether it looks like a complex multiplication or not. And these complex multiplication forms, somehow they appear. I mean, you can count how many there are, but you can just forget about them because they are finitely many. And for example, in the case of a square free level, they do not appear. So it really doesn't matter. And just before explaining all the details of our result, so you see it is a lower bound, then I want to make a remark, is that so some numerical experiments made by Panos show that this number NCM of nk stabilizes when k grows. And this is some phenomena that also appears. For example, you see that there are a lot of elliptic curves. If you look at Cremona tables, or well, the LMFDB tables of elliptic curves, there are many elliptic curves which are forms of weight 2. But when the weight starts growing, then it's hard to find eigenforms with rational coefficients. So somehow it's like the small values of k are not what really happens. Okay, so let me start talking about what is invariants. So first, local invariant. And this is going to be very related to Jessica's talk yesterday, but I'm going to look at it on the other side of the local Lagrange correspondence. So let me give a definition. So a local inertial type of a Bailey-Lin representation tau is the isomorphism class of its restriction to the inertia sub. Okay, and so via the local Langlands correspondence, so this relates to understanding your automorphic representation restricted to GL2 of CP, which is precisely what Jessica was saying yesterday when she was talking about the supercuspidal representations. She was trying to induce things from GL2 of CP, and this is like the other side of the story. But as she was saying yesterday, to understand the supercuspidal representations, it's easier to look at them on the Galois side. That's why we considered we did all the computations on the Galois side. And actually, it's not clear to me if I would have to rewrite the proof on the automorphic side. It's still not clear to me how to do it. I mean, from her talk yesterday, I think there are some things that could be done, but it's not clear whether this will give the right answer. So let me start just recalling the classification. So the advantage for us is that we're only going to work with GL2. So in this case, the classification of two-dimensional Bell-Berlin representations is somehow standard. Two-dimensional Bell-Berlin representations. So first of all, we have the so-called principal series. Which is just a sum of two characters, and the monodromy operator is just trivial, so no monodromy. Remember that we ask our Neven typos to be trivial, so this will impose some conditions on these characters. Then you have another type of representations, which is called the special representations, or Steinberg. Which is also a direct sum of a character times its tight twist, but now the monodromy operator is non-trivial. And this is a tight twist. So it's to multiply the character by the unramified character, whose values at Frobenius is P. So this is Beta representations of GL2 of QP. And then we have the other special ones. So you have the supercuspidal ones, which will be more or less the whole story. And in the Galois side, so they are induced from the Bell group of a quadratic extension, where E over QP is quadratic. And this theta is a character of this Bell group. And you want this representation to be reducible, so you want this to, which does not factor through the norm map. So if you start with a character of the Bell group of Q, and then you just consider the norm map from E to QP, and then you compose with the character, then you will get a representation, but it's going to be a reducible one. So you ask for this extra condition of not factoring through the norm map for this representation to be irreducible. And then you have some sporadic ones, which I think it's a very interesting story. And I will just mention them briefly because I think somehow they are the more interesting ones, but sometimes not so well studied. So this was mostly studied by Bale, Andre Bale. This only happens for p equals to 2. And so the idea is that when you have a representation from your Bell group to PGL2 of C, so this is the projective group. So you know that there are finitely many subgroups of PGL2 of C, and so you have the classical one, and so here you have some sporadic ones. And between the sporadic groups, you know there is an A4 and an S4. Okay. Now since P is 2, we're going to look at extension of Q2. And so actually what Bale proved is that the A4 case does not appear, so there is no A4 extension of Q2. Nowadays you can look at some tables, for example, John Jones and David Roberts tables of local fields, and you can check that there are no extensions of the type A4 of Q2. But actually, if you look at extensions with Galois group S4, so that there are 3 extensions. But these are projective representations, so somehow you'd like to lift them. So here you have PGL2, and then you have GL2. And so you know that here you have this S4, and then what Bale proves that you actually have a double cover of S4, and that to know whether you have your representation with image in S4, and you want to know whether you can lift it or not. And he proved that out of these 3 representations, you actually can lift 2 of them, and this group is GL2 of F3. And so you get some extra representations, and it's not that just that you get some extra representations. Of course, they're going to be all twist of 2 given ones, but he also gave a list of them. And so this is the 2 families. So you see they are twist of each other, so you only can twist by elements at 2. So you can twist by the trivial character, the character corresponding to square root of -1, square root of 2, and square root of -2. That's why you have 4 of them. So they are a quadratic twist of each other. And these GL2 of F3 extensions corresponds to adding the 3 torsion points of these 2 families of these 2 elliptic curves and their twists. And actually you can compute the conductor of the representations, and these are these 2 to the 7th, 2 to the 4th, 2 cubed, and 2 to the 6th. Actually, Bell did not compute the conductors. This was later done in some articles by Pilar Bayer and Arena Rios. I think it's not Arena, but Rios. I don't remember the name. So this will play some role when you try to understand these local invariants at the prime p equals to 2. But for all the other ones, so let me go back to this note. So this only will, you will have to do something special at the prime 2, but for all the other primes, I mean, you can just follow the classical classification. Okay, so what do we do? So first, we want to try to compute local type p to the n, to is just the number, and then we have to see how this matches of local types Galois orbits of conductor p to the n and trivial Neven types. And we would like to compute these numbers. Okay, so let me show you a table and let me explain you how you can compute these numbers. Okay, so here's the values of these representations. So in this table, so PS means principal series, ST Steinberg, and SC means supercuspidal, and then actually you can split the supercuspidal representations in 2 different ones. I don't know how to understand this on the automorphic side, because you can induce the character from an unramified extension, or you can induce the character from a ramified extension. And actually the values of the level or the conductor of these representations are different. In one case, you're going to get even exponents, and in the other case, you're going to get odd exponents, most of the cases. And where sigma naught is just the number of divisors of p minus 1. Okay, so you can compute explicitly. And let me just give you an example. I'm going just to do the easy example because I don't have that much time. But let me show you just an easy example of how do you compute such numbers. And then I'll come back to this table. Okay, so let me give you an example. So let's try to consider the easy case. So let's suppose that our prime is not 2, and let's suppose that the type is principal series. Okay. In particular, we know that our representation is a sum of 2 characters, and we know that it has trivial event typos. So the trivial event typos hypothesis, this implies that when we restrict the first character to the integers, it's going to be the same as the second character inverse restricted to the integers. So you see, so somehow you only have to compute the number of characters of one of them, and then the other one is uniquely determined. And also note in particular that they both have the same conductor, so they only appear at even exponents, which is something that we somehow all knew. You don't get ramified principal series, for example, of level P, only the standard ones appear there. Okay, and so say that the conductor of this He1 is just P to the n. So we know that it factors through a character of C mod P to the n star. So this is a cyclic group of order P to the n minus 1 times P minus 1. Okay. and then if we'd like to compute the order of the character, we know that it's going to be a divisor of P to the n minus 1 times P minus 1. But note that since we want our character to be primitive, because P to the n is the conductor, then we want P to the n minus 1 to divide the order. You see? And so you don't have that many choices. Then in particular, then the order, it's somehow in bijection with divisors of P minus 1. And this works if n is greater than 1. And so the same thing here, but not 1, because if it's of order 1, I don't have the extra power of P, then it's just a trivial character. Okay, and the only remark here is that know that these two characters are Galois conjugate if and only if they have the same order. Right? I mean, it's a cyclic group, so you just have to tell where the generator goes, and the generator needs to go to a dth root of unity, where d is the order, and two primitive dth roots of unity are Galois conjugate of each other. So the order, since it's a cyclic group, the order determines the Galois orbit. And then in particular, with this, you get that if you want to count the number of forms of level P to the 2n, which are principal series, then the number is going to be the number of divisors of P minus 1 if n is greater than 1, and the number of divisors of P minus 1 if n is equal to 1. Because you have to remove the trivial character. If n is greater than 1, actually your character does not have order d, but d times p, or p to the n, and this is why it's still primitive. Okay? So this is just the thing what justifies this first table. You see, so the first row, when you say principal series, when n is equal, so here we're looking at the exponents P to the n, there is a shift because we're considering all of them. So there you get the number of divisors minus 1 and the other of divisors in the other case. And doing a similar computation, you have to be a little more careful with the supercuspidal ones, but you have to count the number of quadratic extensions, and then you have to count how many different characters you get and when to induced representations are different. And actually, if you want to do it for 2, then it's a little more complicated, But you can also compute it. So you have the principal series, the Steinberg, the supercuspidal and ramified, and then you have the two different ramified extensions because there are more extensions on Q2 than over QP, and then you have the sporadic ones. So the sporadic ones are the ones that I was mentioning before. So this more or less has to do with this first part of the invariants that we want to discuss. Okay. So note that what I did here was just trying to compute Galois orbits of Bell-Levin representations or of local automorphic forms, but somehow this we still have to explain why this has something to do with the problem we are trying to understand. So let me talk a little bit about types and this LO that appears in our result. And so now I would like to compare these numbers with the numbers coming from a modular form. So start with a modular form of gamma naught of n, new form. And we know that F is related to an automorphic form, which is a representation, as was also mentioned yesterday in Jessica's talk. It's a representation of GL2 of the Adels over Q. And we know that actually this pi f is a restricted tensor product of some representations pi fp times pi f infinity. So I'm not going to look at the infinity part. We're mostly interested in the local parts. And then if we look at the coefficient field, we know that this is a finite extension of Q. And so somehow we'd like to understand what's the, how I mean, so what we're trying to understand what happens with this pi fp, these local parts here, okay, and these are the ones matching these Bell-Levin representations that I was mentioning before, and we'd like to understand what happens when we conjugate modular forms. What's the relation with the conjugate forms in these Bell-Levin forms? Okay, so let me mention the following little lemma. And actually, I think this is a very interesting one, and it's well known to experts, but sometimes it's not in many classical references. So suppose that the local representation, I'm going just to do one of the cases. Suppose it's a principal series. I mean, we consider all of them in the article. Okay, and suppose that when we restrict our character, so I'm using local class field theory here all the time, but suppose that when we restrict our character to CP star, this is a character of order D. And then the statement is that if you look at the cyclotomic field of the D roots of unity, and you take the maximal totally real subextension, then this is contained in your coefficient field. I mean, this is pretty standard, but sometimes it's hard to find this sort of results in the literature. And for example, you see this is very useful when you want to understand elliptic curves, for example. You know that the coefficient field is the rational, and then you know that if you have a principal series, then the order of the character cannot be too large. And I know that this somehow is telling you that your prime P can only be 2 or 3, or 2, 3, or 5. No, 5 not, 2 or 3. Because otherwise the coefficient field is going to be quite large compared, I mean, it cannot be Q. Okay,
Excuse me.
So somehow, yes.
In the lemma, shouldn't the D, you put the order D, shouldn't it appears in the formula? Or maybe I'm reading wrong.
Oh yeah, no, it's a D. Sorry, thank you.
Thank you.
Yeah, it's a D. Yeah, so it's a divisor of P minus 1. Yeah, thank you, Luis. Okay. So let me have time. So let me give you a sketch of the proof. So how does this work? So suppose it does not. So we're going to try to use some Galois representations. So suppose that this field is not contained in your coefficient field. So now you have some picture which is the following. So here you have like the intersection. Here you have Q. Okay, and so the idea is that I'm going to take a prime L which is not P. I'm going to try to look at some L-adic representation attached to our modular form, and I'm going to choose the prime B such that I want the inertial degree in this extension is not 1. Right? I mean, the whole extension is cyclic, so you have primes that are inert all the way up to Q of, say, of this roots of unity extension. So I'm just going to take any prime such that this is not 1. So in particular, the point is that if I take some lambda in Kf dividing L, then this Q of theta D plus L, the completion about any prime inside L is not contained in Kf lambda, right? Because in this extension here is non-trivial. That's the main point. And then we know that since the inertia at P is a subgroup of the Galois group of Q P bar over QP, and this is a subgroup of the Galois group of Q bar over Q, so you just choose some prime above P. Then we know that there exists some element in the Galois group of Q bar over Q, such that when we evaluate our character at sigma, this is just these roots of unity, right? Because we know that the character on inertia elements has order D, so evaluated at some point, it has to be these roots of unity. But then, in particular, the rho f lambda of sigma, I mean, if this is going to be the direct sum of the two characters, and so when you compute the trace of rho f lambda of sigma, it's just this element, which is a generator for this cube CD plus. Okay, but it's a generator, but then in particular it is a generator of the completion, but this is a contradiction, right? Because I'm assuming that the completion of this extension here is not trivial. So I'm saying that in the coefficient field I have an element that is generating the other one, but the completions are different. So this is a contradiction. Then in particular, this element has to be there. And why is this important? Because then the point is that I know that I do have enough elements in my coefficient field such that when I look at the Galois conjugates, they are going to conjugate the local types. Okay, before we just computed things abstractly. Okay, but if my coefficient field is just Q and locally I have some character which has huge order, I won't be able to look at all its Galois conjugates because I don't have elements to try to conjugate by. Okay, so this is the reason why I need to prove something about how large are the coefficient fields. And then with these results in particular, we can prove the following, is that the following sets are the same. Okay, I think. So on the one side, we can look at these the local components of the conjugate forms. Okay, so I started with a new form. I conjugate the form and I look at the local component at P, and this is the same as the Galois orbits of tau, where I'm assuming that the local type at P is 2. Okay, and so if I want to be explicit here, I should restrict to inertia because I'm only considering the inertial types. Okay, so this, and so somehow this explains why when I look at all these inertia types, at least I'm going to have as many as the ones I mentioned before. So when I look at all the conjugate Galois orbit of F and I just look at the pth part, I'm going to get as many as Galois orbits as I mentioned before. But so this seems like almost all of the story, but actually this is not the whole part. So let me explain to you what is the other ingredient. So also if F is a new form, so there is a nice theory of Atkin-Lehner. So for each P dividing N, there is an Atkin-Lehner operator, which is an involution. And in particular, so for each P dividing N, there exists an epsilon P, which is just a sign. It's a plus or minus 1, such that when I compute the Atkin-Lehner operator on F, it's epsilon P times F. Okay? And so what is really easy to check is that this eigenvalue for the Atkin-Lehner operator is stable under Galois conjugation. So if sigma is in the Galois group of Q bar over Q, then WP and WP of F is lambda P times F. Then WP of sigma of F is, sorry, this should be an epsilon. This is epsilon P times sigma of F. So you see this is another invariant of your Galois orbits. But there is somehow you have to be a little careful here. So let me just mention one example why you have to be very careful here. So this is actually due to Atkin and Lehner. So if you start with a form of weight K for gamma naught of P, I think this works for any weight, and you just take high P to be the quadratic character attached to the unramified extension outside P. Then the root number of the twisted representation is uniquely determined by the congruence of P mod 4. So you see, when you start with the original representation, for example, let's say K is 2, so you have an elliptic curve, you know that the root number can be plus or minus 1. I mean, you have the two of them appearing. But when you twist your form, then you get something which has the same value. It only depends on P mod 4. Okay, so you're losing your root number somehow. But in the original form, in the original family, you know that when you separate different Galois orbits, then the Atkin-Lehner eigenvalue is stable in each one of the orbits. So this implies that when you want to look at this root number, you don't have to look at it in the level you are considering, but you need to go back to the minimal level. Okay, so what happens is that then we need to consider the Atkin-Lehner eigenvalue, not of F, but of its minimal twist. And with minimal twist, what I mean is the twist of minimal level and trivial Neven types. So minimal level is not well defined, you might, if you start with a supercuspidal representation of level p square and you twist it, you get again another supercuspidal representation of level p square, but it really doesn't matter. So if the level doesn't go down, you can just stick to the original form, and if it does go down, then you just take the minimal one. So this is what you want to do. And so now let me define this constant. So this L of p to the n is, by definition, pairs to tilde epsilon, such that this element is a local type Galois orbit. That's why the tilde over it. And this epsilon belongs to plus minus 1, but I want to restrict with the extra assumption that epsilon is a possible Atkins-Lehner eigenvalue for the type tau. Okay, and so let me tell you what I mean with this. So you see, when you want to look at the Atkins-Lehner eigenvalue of some types, then sometimes this eigenvalue is uniquely determined, so it cannot happen that the two of them occur. So for example, if you start with a principal series, or if it's a ramified Sternberg, or if it's a supercuspidal coming from an unramified quadratic extension, then there is a unique possible root number or Atkins-Lehner eigenvalue that might appear in this type. But in the ramified supercuspidal representation, then the two of them appear. And actually, if you start with one possible eigenvalue, and then you twist by the quadratic character, which is unramified at p, then you get the other one. So this is what I mean with a possible one. So if you start with a type of the first kind, then you just choose one of them. But if you start with the types of the second one, then you choose the two possible signs. And actually, you have a similar statement at 2, but it's a little more complicated. And this is why I didn't include it here. Okay, so this is what appears in our result. And somehow, at least I explained the ingredients, and we already counted them. I think I have here the formula. So you can actually try to count how many there are, and then you just take the possible values of the local types, and then you just some of them multiply by 2, and some of them do not, and you add them together, and then you have some different situations depending on whether p is 2 or 3 because of these local numbers. But you have some concrete value for each prime p, and this is the quantity that you have to plug in the first in the theorem. So we're almost there. So what are we missing? So then to prove our main result, then we need some existence theorem, local types theorem. So what do I mean with this? Well, we know how many local types there are, but then we need to prove, for this to be a lower bound, we need to prove that given a local type, there is one new form of weight k with these local types. And this is where our extra hypothesis appears. So let me just state this. This is a theorem, and this is mostly due to Weinstein, by Kimball Martin, and by Kim, Shin, and Templier. And what it says is that given, so you just take a bunch of local types and root numbers, as before, then there exists a new form in Sk of gamma naught of n, such that, so the local type is the one you specified. The root number is the one you specified, and F does not have CM. And for this, provided that N is a prime power or square free. So our hypothesis comes from this extra existence result, and somehow, so asking for the first condition uniquely, then you don't have any hypothesis on the value of N. But if you want to include the Atkin-Lerner operator, then this is the part that it's missing. So we're trying to extend the results. I mean, since they were not interested in this sort of problems, this is why this is the cases we can get. But we're thinking about extending this result to any number, and then our result will work for any value of N. And so then the corollary, or the main result, is that if you take the product over P divided N of these numbers, then this is less or equal than the number of newforms if K. I didn't say for K large enough. So you can actually say something on the bound. We did not try to do it, but you need, for this existence result, you need K to be large enough. And so let me just make a remark, because most of you will be thinking, how good is this? So the inequality is not sharp. So this is the first things that you should know. And actually, we can improve it. And so I want to just give you one example. I may take 1 or 2 extra minutes. And why can we improve it? And so let's suppose that you start with your level N, which is 11 squared times 31 squared. Of course, this is somehow out of the computable range. And then you look at your type at 11 to be principal series with the character of order 5. And then you take the local type at 31 to be exactly the same thing here. And then what we proved is that this quadratic extension is contained in your coefficient field, okay? But what is the issue here? Well, when we look at the prime 11, so we have a Galois orbit that we would like to conjugate all of them. So we have 4 different characters of order 5. And we know that we can conjugate all of them to move from one to the other. But once we choose one of them, we cannot change the Galois orbit at 31 because we already choose the character at 11. So when you do this separately, then you're thinking that you have enough elements to conjugate as if the primes were completely independent of each other. But these are related. I mean, there is the same, you need the same guy to conjugate at 2 different primes, okay? But so up to conjugation, then you can choose that your at 11, then the character at, I don't know, some generator, it's, I don't know, a 5th root of unity, a generator of inertia. But if you do that, then when you want to look at the type at 31, your character at the generator can be any of the possible 5th roots of unity, primitive 5th roots of unity. And so here you do not have control. So even our bound would say 1, actually we can prove it's at least 4. Okay, so then our bound gives 1, but is at least 4. So actually we could write a much better statement, but it's a really complicated one and a combinatorial one. So actually our proof gives itself a better statement. But in the case of prime power, then it's actually the best you can get. And we don't know, but a remark is that the data seems to suggest that at least for prime power, which is the easy case to taste, our lower bounds are optimal. And I'm not making any statement here. I'm not saying this is any sort of conjecture. Panos made some sort of conjecture in his article, but I mean, we don't have any theoretical reason to believe this is the case. We can only say that we tried many experiments looking at Panos tables, and the lower bound seems to be optimal. There is some discrepancy at 2 that we still do not understand, and actually our bound gives the bound is differs by the number by 2, but we don't know why this is the case. So I think I'll stop here.
Okay, thank you, Ariel. Are there questions for Ariel? No? Okay, if there are no questions, we thank the speaker again.